So my talk will be about a joint work with Massimiliano Berti, so concerning almost global solutions for the periodic gravity capillarity equation. So we consider a fluid, say water, which lies between a flat bottom, given by this line, and a free surface, which is a graph of some function y equals eta of t and of x. So this function eta will be periodic, and we assume that the fluid is incompressible and irrotational. So that in the water, the velocity of the fluid will be given by the gradient of some potential phi, and phi will solve the Laplace equation, Laplacian phi equals 0. And we assume a boundary condition at the bottom, which is that the normal derivative of phi should vanish. And so if we are given the value of this potential on the free surface, we may, solving this equation, deduce the value of phi and so of the velocity everywhere. So the motion of the fluid is determined by the function eta and by the restriction psi of capital phi to the free surface. And so if you write the early equations inside the water, and if you write a convenient boundary condition at the free surface, you get an evolution equation for eta and psi, which is the so-called Craig-Sulem-Zakharov formulation of the gravity capillarity wave equations that I describe now. So the first equation in that system is dt eta equals g of eta psi, where g of eta is the Dirichlet-Neumann operator, which is defined in the following way. So given function psi, you solve the Dirichlet problem with boundary value psi, and so you find a potential capital phi, and then you compute the normal derivative of that potential, dy phi minus dx eta dx phi, at the free surface y equals eta of t and of x. And this defines g of eta psi, which is just the usual Dirichlet-Neumann operator. The second equation says that dt psi is given by some complicated expression, say minus g eta minus 1/2 of dx psi to the square plus g of eta acting on psi plus dx psi dx eta to the square divided by twice 1 plus dx eta to the square plus kappa h of eta, where h of eta is some explicit function that's the direct derivative of eta prime over square root of 1 plus eta prime square, eta prime denoting just dx eta. And so we have two parameters in that equation, namely g, which is the gravity, and kappa, which is the surface tension. So we shall consider these equations when x belongs to T1, that is, we consider these equations with functions which are periodic in x, and we want to solve that system for long times. So let me give some known results. So I shall not read all the names which are on this slide. I will just say that concerning local existence theory for the preceding system with smooth enough data, the most basic work was due to Sijue Wu, was proved that when x belongs to R or R2 instead of T1, when kappa, the surface tension, is 0, and when the fluid has infinite depths, that local solutions exist over some time interval. So then there have been quite a lot of other works treating different other cases. The only one I shall mention explicitly is the one of Schweizer, which obtained local existence in the periodic framework for finite depths and for positive kappa. That is the problem we're interested in. And then there have been quite a lot of works devoted to long-time existence when you consider small and decaying data. So in that case, you may exploit the dispersive properties of the equation so that the solutions of the linearized equation will decay when time goes to infinity. And this allows you to prove that if moreover the data are small and smooth, then you may get a solution defined over a long time interval and even in some cases global solutions. So I shall not read all these name of contributors. I will just say that there are nevertheless also some results which have been obtained when you consider a periodic, not necessarily periodic, but say data which do not decay at infinity by Ephraim and Tataru, and also by Alazar Burke and Zuili. And well, it has been shown in different cases that, say, for instance, for a periodic Cauchy data, you have a so-called cubic lifespan. That is, if you take Cauchy data of size epsilon, you get solutions defined over an interval of time of length epsilon to the -2, while local existence theory provides a solution defined over an interval of time of length epsilon to the -1. And so what we want to do is to try, under convenient assumption, to do better than getting this cubic lifespan.
Why do you call it cubic and not quadratic?
Well, you should ask this question to Daniel and Mihaela Ephraim. I guess that this is because quadratic, this corresponds to a quadratic nonlinearity. And then when you have local existence theory, you get 1 over epsilon. If you have a cubic nonlinearity, you get 1 over epsilon to the square. But of course, here the nonlinearity is quadratic, and nevertheless, you get this cubic lifespan. So that's why the origin, I guess, of the terminology. So let me give the assumptions we shall be working with. Let me introduce some operator, just this matrix S, which is a matrix 1, 0, 0, -1. And let me say that a solution, eta psi of our capillarity gravity system, is reversible if and only if, when we compute the value of the solution at time -t, it is equal to the matrix S acting on the solution computed at time t. So of course it follows immediately from this equality that if this property holds, then the second component, psi, has to vanish at time t equals 0. And conversely, if you start from a Cauchy data whose second component vanishes at time 0, then your solution will be reversible, that it will satisfy this equality. And this just follows from the fact that your equation may be written as, say, eta dot psi dot equals some function f of eta psi, where f has the property that making act this matrix S at the left on f of eta psi, you get something which is equal to minus f of s of eta psi. And so you deduce immediately from that property that under that assumption, the solution is reversible. And so to state the main theorem, I will use this property of reversibility, and I will use also a couple of notation that I introduce now. So we shall look for the first component, eta, of our solution in a Sobolev space, Hs plus 1 over 4, of T1. So periodic functions which are Sobolev on each period. We shall assume, moreover, that these functions are even, and we shall assume that the average of eta is 0. So if these properties are satisfied at the initial time, then they hold for any positive time as a consequence of the structure of the equation. So concerning the second component of eta psi, we shall take it in a space, a Sobolev space, H s minus 1 over 4, of even functions on the torus, on T1. And actually I'm taking an homogeneous Sobolev space that is a Sobolev space modulo constants. So we do that because the system is actually well defined on functions modulo constants. So we may consider the second equation of the system, the one on psi, as projected on functions modulo constants. And it's natural to do so because actually only the gradient of psi, if you want, has a physical meaning, not psi itself. And now that I've introduced these notations and definitions, I may state the main theorem. So the theorem says that you may find a zero-measure subset, capital N, of 0 plus infinity to the square. And for any couple G kappa of gravity and surface tension taken outside this subset of zero measure, for any given integer capital N, there is some index of regularity as 0, large enough, such that if you take any s larger than s0, well, you may find some positive constants, c, epsilon 0, such that for any epsilon smaller than epsilon 0, for any function eta 0 in the Sobolev space that I introduced above, with 0 average and even, with norm in that space smaller than epsilon, if you solve your capillarity gravity system with Cauchy data at t equals 0 given by eta 0 and 0, then you get a unique solution, continuous on some interval with values in the natural Sobolev space, where the length of the interval of existence is bounded from below by c epsilon to the minus n. So in other words, the theorem says that you may get almost global solutions, that is, solutions defined on an interval of length epsilon to the minus n for any given a priori n. If you take Cauchy data which are small enough, which are smooth enough, which are reversible in that sense, in the sense that the second component should be 0 at t equals 0, and if, moreover, you have taken your parameters outside some exceptional subset of zero measure. So before giving some elements of proof, let me make a remark, which is that actually you may reduce to the case when G equals 1 just using the homogeneities of the equation, and then the parameter that you take outside a subset of zero measure is just the parameter kappa. And let me say also that this theorem provides almost global solutions for the Cauchy problem under the assumptions that I indicated. We do not know if one can obtain global solutions for the Cauchy problem.
Or e
but,
to the 1 over epsilon.
Sorry?
Or e to the 1 over epsilon. Or
or even e to the 1 over epsilon. We do not know that. But there are, on the other hand, there are non-trivial examples of global solutions, that is, time quasi-periodic solutions, which have been constructed by Berti and Montalto, and which will be the subject of the talk of Massimiliano tomorrow.
But
is it with zero boundary? So your initial data is special.
The initial data is special because we want to have these reversible solutions So this corresponds to functions which satisfy the properties that I wrote before, eta psi times t equals, okay.
No problem, but if you don't want.
No, but we need these
Yes,
assumptions,
I
and
know,
I shall
I
explain
know
why
what
later.
you need, but is it true or not, you think?
Well, you know, I'm not the kind of person who's making conjectures on the air, so I will not.
So what
What is free physically?
No, psi.
Psi.
No, psi physically, that's the restriction of the potential
What?
to the restriction of the potential to the free surface.
So if it's zero, then there's zero initial velocity. You raise the surface and then you let it go, but with no
Okay,
initial
so there is
velocity.
no.
Okay, so now we shall, in a first step, try to forget the explicit expression of the equation and reduce ourselves to some parallel differential formulation. So, first of all, let me fix some notations. So, if A is a symbol, so say a function of x and psi, such that d psi beta A is bounded from above by psi power m minus beta for a given m and any beta, one associates to this A an operator, a parallel differential operator, in the following way. One takes chi, some cutoff function with small enough support equal to 1 close to 0. And one defines from the function A a new function, A chi, in the following way. One takes the Fourier transform of A relatively to the x variable. This gives A hat of x hat psi. One multiplies by the cutoff chi of x hat over psi and takes inverse Fourier transform. And then in that way, you define the Bonnivet quantization of the function A as the operator associating to some test function u, a new function given by this integral 1 over 2 pi integral e to the I x minus y xi, a chi of x plus y over 2 and of xi, u of y dy dxi. So in that way one gets an operator which is bounded from hs to hs minus m for any s. If you assume, moreover, that your symbol A is periodic in X, your operator will send periodic functions of hs of t1 to functions of hs minus m of t1. And then, using the celebrated Bonni's parallelization formula, you may rewrite your equation, the equation we started from, as a parallel differential equation. That is, you may write the initial equation under the following form. You have capital dt, where capital dt will be 1 over I d over dt, minus the operator associated to a matrix of symbols, capital A. These symbols depend on eta psi because we treat a nonlinear equation. And all that operator acting on the unknown eta psi should be equal to some smoothing operator, that is an operator that will gain rho derivatives for rho a given large number that we may choose if we work in spaces of smoothing functions acting on eta psi. So usually when you do that from a nice quasi-linear hyperbolic equation, you end up with a system for which you can get easily some energy estimates and then eventually local existence theory. Well, in the case of the water waves equation, it is well known that when you do that, you get into trouble because the matrix of symbols A that you get has eigenvalues whose imaginary part goes to infinity when psi goes to infinity. In other words, you have instabilities which prevent you from getting energy estimates without derivative losses from such a formulation when you apply this polarization method to a water waves equation. So this problem has been solved years ago. First of all, by C.J. Wu, who designed some Lagrangian formulation of the equations that allow one to overcome that difficulty.
Can I say something about that? That Nalimov invented that.
Yeah, but it was for small data. But
It's the same formulation.
Yeah, okay.
It's the same calculation. Same formula.
so then there has been another approach that has been used, relying on the so-called good unknown of Alinac by Alazar-Métivier, Alazar-Burgzvili, Lannes. And this is the method we shall adopt. And then, more recently, Anterifrim and Tataru proposed a third approach using some holomorphic coordinates. And so we shall use, as I said, this good unknown approach, which consists in saying that this problem that I was mentioning comes from the fact that we didn't use the good unknowns to express the problem, and that instead of writing the equation on eta psi, as I did, one should introduce instead omega, which is psi minus, well, some operator acting on eta, where b, the symbol of this operator, is just a function, an explicit function, g of eta psi, plus dx psi dx eta divided by 1 plus dx eta to the square. And it turns out that if you write the system in these unknowns, then things are much better. So more precisely, if we start from eta psi, a solution of our equation defined on some time interval, let me introduce a complex unknown in the following way. Call lambda kappa of d the operator d hyperbolic tangent of d divided by 1 plus kappa d squared to the 1 over 4. This is an operator of order minus 1 over 4. And define from the good unknown omega and from eta a complex valued function u, which is just lambda kappa of d omega plus I lambda kappa of d minus 1 eta. Next, introduce capital U, the vector u bar, and write your equation under a paradigmized form on capital U. So when you do that, you obtain the following. Well, capital dt minus the operator with symbol, a new matrix of symbols, capital A of u dx psi acting on u, equals some smoothing operator r of u acting on u. And now what is important is the information we have on the structure of that matrix A. So A is a matrix of symbols of order 3/2. So the main contribution in terms of the order is given by some Fourier multiplier, m kappa of psi, where m kappa of psi is given explicitly by psi hyperbolic tangent of psi power 1/2 times 1 plus kappa psi square to the 1/2. So this is a symbol of order 3/2, which is multiplied by 1 plus zeta of utx, zeta being some real valued function, multiplied by this matrix, 1, 0, 0, minus 1. And you have also another contribution of order 3/2, m kappa zeta, multiplied by a matrix 0, minus 1, 1, 0. Then you have also contributions of positive but lower order, namely lambda 1/2 of u times some matrix, and lambda 1 of u times the identity matrix. These two symbols are of order 1/2 and 1 respectively, so they are of positive order, but it turns out that their imaginary part is of order j minus 1, so of negative order, well, or at least non-positive order for lambda 1. And then you have contributions of non-positive order given by symbols lambda minus 1/2 of order minus 1/2, lambda 0 of order 0. And what is important here is that when you compute the eigenvalues of that new matrix, you get that the imaginary part of these eigenvalues is bounded when psi goes to infinity, which was a property which was not true in the initial formulation. And this property comes from the fact that using this good unknown, you make appear a symbol lambda 1/2 here, which has the imaginary part of negative order, while if you are doing that starting from the initial unknowns psi and eta instead of omega and eta, you would have got a similar expression, but the imaginary part of this symbol would have been of order still 1/2, and this is what would be responsible for the fact that the eigenvalues of the matrix would have had imaginary part also of order 1/2 that may go to infinity when psi goes to infinity, and this is the point that creates instability in the initial formulation. So now that we have this form of the equation, let me also introduce 3 properties satisfied by the matrix of symbols A that will play an essential role. So recall that I define reversibility using some linear operator S. And now I will call S the matrix minus 0, 1, 1, 0. That's just a translation of the same operator, but on the new basis we are using in the complex formulation of our equation. And the matrix of symbols that you get for the expression of your system satisfies 3 properties. The first one says that if you compute this matrix of symbol A at u, t, x minus xi and conjugate it, you get minus S A of u, t, x, xi, S. So this property just means that when you consider the associated operator, make it act on V and take the conjugate, what you obtain is minus S, the operator with symbol A, acting on S, acting on V bar. And this property is a property that just reflects the fact that we are working with a system on capital U, which is U bar, where the second equation of the system is obtained from the first one by conjugation. So this is just a property coming from the fact that we started from an equation, from a system with real valued functions. The second property satisfied by the matrix A is that A of u t minus x minus xi is equal to A of u t x xi. And this means that the associated operator, in particular, preserves even functions, which is a property we need since we shall be working with even functions. And finally, the third property is the so-called reversibility, which says that if you compute the matrix A at SU t x xi, it is equal to minus S A of u t x xi S. So the meaning of this property is as follows. If you consider the right-hand side of our system, which was op A of u acting on u, and if you apply to it S, this is equal to minus the operator with symbol A of SU acting on SU. And this just reflects the fact that the system is reversible. The properties that I used before when I wrote that S of some function f of eta psi was equal to minus f of s of eta psi. So that's the third property we shall be using to obtain the result of long-time existence. And now let me give some ideas on the proof. So the first step is a sequence of reductions that have been used in other contexts by Al-Zarbaldi, by Berdi-Montalto. So I will not give any detail about these reductions. I will just say that making a diagonalization of the symbol of your operator, and then making some change of variable, or actually some para-composition, and making conjugations by convenient Fourier integral operators, you may reduce the system that I wrote before to a system which has constant coefficients. So in other words, you may introduce some new unknown, capital V, that may be expressed explicitly from U, that will be of the same size of U in HS when both terms are small enough, and such that this new unknown will solve a new equation that may be written as follows. So you have capital dt minus m kappa of dx, the Fourier multiplier that I introduced before, which is dx hyperbolic tangent of dx to the 1/2 1 plus kappa squared dx squared to the 1/2 times some function 1 plus zeta underline of u and of t, which is only a function of t. So this operator is a constant coefficient operator at fixed time. So this multiplies the matrix, diagonal matrix 1, 0, 0, minus 1. And then you have another operator, capital H of u, t, dx, where capital H is also a diagonal matrix of constant coefficient Su differential operators, which are over the 1. And what is important is that the imaginary part of the symbol H is over the 0, while H itself is over the 1. And finally, this operator H satisfies the properties, the three properties that I introduced before, the reality, parity preservation, and reversibility conditions. And in the right-hand side of the equation, you have R of u acting on V, where R is again some smoothing operator that satisfies also these three properties. So in other words, we have reduced ourselves to a new equation where in the left-hand side you have just constant coefficient operators. And so it's very easy now to get energy estimates on that equation. Well, actually, when you make an energy estimate on such an equation, the real part of H gives a self-adjoint operator, which disappears in energy estimates. And so what you are left with is just contributions coming from the imaginary part of H, which is an operator over the 0, so an operator which is bounded on L2. And moreover, since we have constant coefficients, we may commute as many derivatives as we want, and so we can write as well L2 or Sobolev energy estimates. So in other words, if you write on the preceding equation a very basic energy estimate, you get that the Sobolev norm of the solution at time t is bounded by the Sobolev norm at time 0, plus constant the integral from 0 to t of the operator imaginary part of h of u tau dx acting on v at time tau in hs d tau. So if we knew, in addition, that this symbol, imaginary part of h, not only is over the 0, but that it vanishes like norm of u in hs to the n when u goes to 0, then the proof will be finished. Because in this case, we could write the preceding inequality saying that the Sobolev norm of v at time t is bounded by the Sobolev norm of v at time 0 plus an integral from 0 to t of say norm of u at time tau in hs power n, norm of v at time tau in hs d tau. And since we work with Cauchy data of size epsilon, and since we aim at propagating the fact that the solution stays of such a size over some time interval, morally in this interval, this norm of u to the n is of size epsilon to the n, so that some elementary bootstrap argument will show you that if you consider this inequality only for times smaller than c divided by epsilon to the n for small positive c, then you will be able to prove an a priori bound saying that the left-hand side is more than k times epsilon, where k is some fixed constant. And so this a priori bound will tell you that the solution may be extended up to such a time. But of course, to do so, we will need to have this property that the imaginary part of A vanishes like a large power of u when u goes to 0. And this is not true. Im h vanishes like u power 1 when u goes to 0. So we have to do a first step in order to arrive to such a property. And so this step will be a normal forms method. So to explain this, let me call B of capital U xi some diagonal matrix of symbols over the 0 to be determined. And let me look for, again, a new variable, a new unknown, v tilde, given by the exponential of b of u t dx acting on v. So in other words, I'm starting from the equation that was on the preceding slide, namely dt minus m cap of dx times 1 plus zeta underline 1 0 0 minus 1 plus h of u t dx acting on v equals some smoothing operator acting on v. And what I'm doing is just that I intertwine this operator by this exponential. So since I have constant coefficients operators, this exponential of b of u t dx commutes with all these operators. And so when I'm making the conjugation of this equation by this exponential, the only new contribution that will appear will come from the conjugation of dt with xb. That is, I will get another term dtb of u t dx. So that the new unknown v tilde satisfies an equation which is capital dt minus dtb of u t dx minus m kappa of dx 1 plus zeta underline 1 0 0 minus 1 plus h of u t dx v tilde equals r of u v tilde. And now what we have to do, since I recall that what we want to do is to get rid of the contributions to the imaginary part of h that are vanishing when u goes to 0 at the order lower than some u to the n for a given n. So in other words, what we want to do is to choose capital B such that this term will cancel the contributions coming from imh that do not vanish at large order when u goes to 0.
So why do you worry only about cancelling the contribution from H and not R?
Oh, no, of course. I have also to do the same thing for R later. Of course. But here the method is pretty much the same in both cases, and so I explain it on H. So I have to choose B so that dtB minus I imaginary part of H of u dx psi should vanish like u to the n when u goes to 0. So to construct B, I'm looking for it as a sum of expressions Bp of u, which are homogeneous of degree p, p going from 1 up to n minus 1, the last degree that I want to cancel out, each Bp being some p linear map that are restricted to the diagonal u equals u1 equals u2, etc. So now let me compute dtB. When I compute dtB, the t derivative will act successively on each argument of Bp, and I will replace the corresponding dtu using the equation, which was that dtu is some Fourier multiplier m kappa of dx times some matrix K, which was 1, 0, 0 minus 1, acting on capital U, plus some nonlinear terms, which will generate contributions of higher degree of homogeneity. So if I write what I get at the level of the contributions homogeneous of degree p, so I will get Bp, in which I have replaced one of the arguments by the linear part of the equation, this j corresponding to the place of this argument going from 1 to p. The nonlinearities will give terms of higher degree of homogeneity that I may forget at that level. And I want to choose Bp in order to get rid of the contribution to imh homogeneous of degree p that I may write as some imaginary part of hp of u dx I. And now this is essentially the equation to which I reduce myself to finish the proof. So I wrote again that equation at the top of this slide. And to solve it, let me decompose each argument, capital U, as a sum of pi, as a sum in n of pi n plus capital U plus pi n minus capital U, where what I denoted by pi n is just the spectral projector associated to the nth eigenmode of the Laplacian on the circle, and where, since capital U is a 2 vector, the plus and the minus denote projection on the first or the second component on that vector. So if I replace each argument U by such a decomposition, and if I look at what happens when I make act this operator on, for instance, pi n plus capital U, one sees immediately that the result of this operation acting on such a localized function is given by multiplication of the function by the symbol m kappa computed at n. So in other words, when we write the preceding equation, replacing the arguments by pi n1 plus u, pi nl plus u, pi nl plus 1 minus u, up to pi np minus u, when you make act this operator on one of the first L terms, you just get multiplication by m kappa of nj with a plus sign. And of course, this multiplication by a function may move out of BP by linearity. In the same way, for the last terms, when you make act such an operator on the last terms, you get multiplication by some m kappa of nj with a minus sign. So that finally, when you compute this left-hand side, where you replace each argument by a spectrally localized one, what you obtain is just BP computed at these arguments multiplied by some function, dl, which is just given by this sum from m kappa of nj from 1 to L minus the same sum from L plus 1 to P. So our problem is to determine BP in order that the equation be satisfied, and so we have just to divide by dl, and so we have to know that dl is not 0. So clearly there is a case when dl will be 0, whatever you do, which is a case when you have the same number of terms in both sums, and when you have 2-by-2 cancellations between one term in the first sum and one term in the second one. This may happen. In this case, dl will be identically 0. And so I have to distinguish two cases. The first one being the case when such a scenario does not happen. So let me assume that I am not in the preceding case. That is in the case when P is even, L is P over 2, and the set N1 and L coincides with NL plus 1 and P. Since in this case, dl, the function dl vanishes identically. So the lemma says that if you are not in this case, then if the parameter kappa, surface tension, is taken outside the convenient subset of zero measure, then you may ensure a small divisors estimate saying that not only dl does not vanish, but moreover, dl is bounded from below by a constant times n1 plus etc plus np power minus some integer n0. So in other words, when we are not in the forbidden case, we shall be able to divide by dl. That is, we shall be able to solve the equation we were interested in, dl times bl equals I imaginary part of hl, since dl does not vanish. So of course, when we make such a division, we lose some large power of n1 plus np, which means that we lose some derivatives on the coefficients of our equation. But this does not matter because the coefficients of the equation are low frequencies, and that is, we may afford to lose a large number of derivatives on these coefficients if, of course, we work with smooth enough functions. Okay, so this solves the equation we wanted to study in the case except in the case P even, L equals P over 2, and N1 L equals NL plus 1 NP. As we have seen, in that case, this dl will vanish identically whatever the value of the parameter kappa. And so to solve the equation in that last case, we use the three properties that I was mentioning: reality, parity preservation, and reversibility. Because combining these three properties, one may check that the right-hand side of the equation, im HL, or well, im HP in this case, computed at pi 1 plus u up to pi np minus u, with n1 and p satisfying this equality, vanishes identically. So that in the remaining case, the equation to be solved was just 0 equals 0, and we know how to solve such an equation. And so consequently, we have been able to solve in all cases this equation. And we have seen before that solving this equation was allowing one to eliminate the contributions to im HL which have a low degree of homogeneity, and that doing that we are able to get by energy inequality our long time existent result over an interval of time of length epsilon to the minus n, n being the level at which we stop this process of elimination. So this concludes so the proof of the theorem, and this concludes also my talk, which is fortunate because my time is essentially over.
Thank you very much. Are there some questions?
So that's a very interesting cancellation in this reversible and parity setting. So in the general case, that is allowing cosines and sines of x, I mean, because those somehow from my Hamiltonian point of view, those terms are very important, and those are ones which really are important to the dynamics.
You keep them.
And so I imagine that they what cause the action frequency non-degeneracy. So I'm just wondering what happens in the general case.
So in the general case, you know what one is able to do in other settings, and what one would like to be able to do here would be to use the fact that the equation is Hamiltonian, and then the terms that you cannot eliminate the terms for which this dl vanishes correspond to terms depending only on the actions. So these terms, so these terms, they cannot grow. Their Sobolev norms do not grow because they depend just on the actions. And so these are terms that you do not need to eliminate in a Birkhoff normal form using the Hamiltonian character of the equation. And so why didn't we use this approach? Well, this is because of the good unknown that I introduced before. When you pass from the initial unknown to the good unknown, the reversibility condition is trivially preserved. But the point is that the passage from the good unknown to the new from the old unknown to the new unknown is not something that is Hamiltonian, or at least we do not know to do that in an Hamiltonian way. If we could say design some Hamiltonian way of doing that step, then I'm pretty confident that we could write the whole proof in the Hamiltonian framework, and so get rid of these conditions of parity and reversibility.
Sorry? Okay, I think this answers the question. And I have some other questions.
But that doesn't work in this case, in any case.
Sorry?
That would not work in this case. You have to go to another another point of view.
Some other questions. Maybe I have a short question concerning this property, the one you proved. So usually the papers I know, the parameter is in the zero order term of the symbol. So here your kappa is in the main part of the symbol, right? So it's something which I never saw. It makes really a difference in the analysis, or?
Well,
You didn't mention much about this minoration DL. How you prove it?
Oh, so no. So this follows from essentially from some old result with Jérémy, which was applying to say to some general functions, subanalytic functions satisfying some conditions. So the fact that it depends this m kappa, which was written here. So the fact that this, the fact that the kappa here is in front of a derivative of I order does not matter at all in the proof of this lower bound. What is important is the fact that when you consider this function as a function of psi, the dependence on kappa is essentially a non-trivial dependence. And this is what allows you to obtain this small divisors estimate, that is to say that when you evaluate this, or actually what I call DL only at integers, then moving a little bit kappa, you may arrange so that these lower bounds are satisfied. So the fact that kappa is here or here does not matter at all. Actually, you could, factor out kappa and get a parameter here, and it won't change anything.
I see. Okay.
In terms of the method of proof, can you make a comparison with the result of the Taro and thing? Which was an O of epsilon.
The basic point, the basic starting point is the same, that is, you want to get rid of terms of lower degree in the nonlinearity. So to get their cubic result, you have to get rid of the quadratic term of the nonlinearity.
Don't have parameters in the result. There is no
Oh, no. In their case, there is no parameter, but this is because this is
they don't have
for the.
parameters, you have parameters. That's
Yeah, but the point is that they don't have parameter because it's at the level of the quadratic nonlinearity, for which you will have essentially no resonance.
no.
And they don't
But
need
when you-
disparity condition also.
Sorry?
They don't need disparity condition also.
They don't need disparity condition, but disparity condition actually we need it only to deal with the terms, the bad terms, the ones for which you cannot make non-zero your function dl, and so you need it only to get rid of terms of odd degree in your nonlinearity. You need it to get rid of a cubic term. You do not need it. You do not need it to get rid of a quadratic term or a quartic term.
Okay, so up to those cubic terms, the proof will be the same.
Yeah, except that it's not exactly the same framework because.
Point in Tau and Fm is they don't have zero measures, they have every kappa.
Yeah.
And you have kappa except zero measures.
Yeah.
That's important difference.
Yeah, of course. Yeah, so would you be able to recover that result? In other words, without the generic condition.
Well, I suppose we could, but we didn't try to write it down. We wrote, the general thing